All right, children. First chemistry test. How exciting is that? Mr. O'Malley has put objective on my list. You can go check it out. And he asked me to give you an historical point of view about all the objective for your first test. So if I'm going to go from the first to the last, I'm going to go in terms of numbers. All right, so the first objective is to define mass and to define volume. Okay, mass is the amount of matter in object. Easy. Volume is the amount of space. Matters. Takes. All right, so I apologize for my bad writing. I don't think my writing level has gone beyond the third grade. But those concepts were found very quickly in ancient Greece. Okay, sorry. Scientists has measured matter. So that's a pretty easy objective in terms of a historical point of view. What is interesting, and I just said that I will go from in terms of 1 to 8, but I'm gonna jump right now because I'm realizing that you can talk about density right away. So if you see on the objective sheet, you're gonna see a number 1, and I'm gonna jump straight to number 5 because mass and volume, if you relate them together, right? And scientists have done that. They say, well, what if, right? You find a relationship between mass and volume. And that's what they did, right? They realized that if you take one type of matter, for example, one specific type of plastic, right? You change the volume or you change the mass, the volume will change in a proportional way, in a direct proportion, which means, let's say they took a few values of that plastic, right? And they measured the mass and the volume. So they probably found something like this, right? And they found the best line, the best graph that goes through that, and realized, say, oh my God, it's a slope. It's a straight line in a slope, which means it has a direct proportion. What does that mean? It means that the mass is directly proportional to the volume. Now you saw I just do some kind of a Jesus fish. That sign means that it's proportional, all right? Which means that they are directly proportional. That means if you increase the mass, you increase the volume. If you decrease the volume, you decrease the mass. They go together, right? And they realize that, well, you need a constant, right, that binds it together. Once you have a direct proportion, you need a constant to bind it together. Where do you find that constant? That's the slope of the graph is your constant. And in this case, they realize that this is what we call the density. Density is the amount of mass. The amount of mass an object has in a specific space. In a specific space, so a specific volume. Okay? So, density is the slope of your graph, and you know y is equal mx, right? So, y is equal mx. So, in this case, the y will be m. Oh, I messed that up. Okay, it will be m for mass is equal density times v volume, right? See? The slope is the density. And if you rewrite this equation, is the density is equal mass over volume. How fantastic is that? I just did number 1 and number 5 together. And of course, your objective says, write the equation of the line and state the meaning of the slope. So I just did all this. And then you can use numbers to make calculations. Okay, so, all right, that is awesome. I love this. Now, I need to erase everything because I'm going to move to the next one. This is so much fun. You have no idea. Okay, so the next one is developed from experimental evidence, the law of conservation of system mass. So what does that mean? The law of conservation of mass. Remember Lavoisier? I'm going to go from a historical point of view, right? Lavoisier realized that, matter does not disappear. Actually, let me rewrite this. Let me rewrite this in English. English is not my first language. So, matter cannot be created nor destroyed. Oh, my writing is so bad. Okay. It can only change. How did he do that? The same way you watch the different videos, Unit 1, Lab 1, and the slides and all that and the worksheet, right? For example, right? If you have water, you put it on a balance and it's 100 grams of water, right? Right? Let's say you put some fire under it, and now it turns that now it's all gas. So I'm gonna put particles, right? So now it's gas. It's water gas. If you weigh it again, it should be 100 grams. So matter has changed. It has changed, right? But it's the same. Water didn't disappear. Water didn't appear out of nowhere. You still have 100 grams, right? So that is what I did here is a physical change. I apologize. I know I told you I would go chronologically, but I'm not. I'm just skipping from thing to thing, but I just think it's interesting, right? It's a physical change, a change that does not alter the chemical makeup. Alter the chemical not constitution. I don't want to talk about constitution because I don't want to get into politics here. But chemical makeup. I'm saying chemical make. Oh, all right. So that's one example. Another example. I could have used ice melting also. That would have been the exact same, right? Ice as 100 grams. If it melts, then the water in the liquid form now is still 100 grams. Correct? Yes. Now, let's say you have water, right? You weigh it to be 100 grams, right? Again. And then you have a tablet of Alka-Seltzer. That's about 5 grams, okay? All right? You put it in there. What happens? Bubbles. Now you say, but the bubble's gone, so it's going to be less, right? But let's say, and that's what Lavoisier said, well, it's the mass is going somewhere. We're losing mass, and something's happening. But he said, but what about you seal that thing? You seal it, all right? So now the gas cannot escape. So now you put the Alka-Seltzer, right? What should be the mass? It should be 105 grams. And that's what Lavoisier realized. Okay, he realized that. He was like, oh my God, I can do any change to the thing as long as the system is closed. You need to have closed system, right? As long as the system is closed, right? Whatever change you're going to make to that system, the amount of matter will not change. And that's the law of conservation of matter, of conservation of mass. Because matter, mass is just a measurement of matter, correct? Awesome. So that's what Lavoisier did. Actually, Lavoisier was Actually, I told you exactly what he did. I think shared that with some of you. Actually, what Lavoisier did was candle. Thank God you guys left me smaller to show you how to draw, because me, it's not as bad as Silly. I was watching him last night. It was a bit embarrassing what he's trying to draw. He put in a seal. Oh, whoops. Not yellow. Let's go back to black here. Put in the seal, right? And he let it go. And he realized that, let's say it was 5 grams, right? Over time, stayed 5 grams. After 1 day, after 2 days, 5 grams. As the candle was getting smaller and smaller. I was like, oh my God, wow. So, law of conservation of mass, okay? Awesome. Let's go to the next one. I'm being incoherent here. The Alka-Seltzer in the water was a chemical change. Chemical change. A chemical change is a change that alters. Oh, I cannot write to save my life. Is a change that alters the chemical makeup. You know, in this case, what happened is that you add H2O, you add the Alka-Seltzer, right? You get a gas. The gas is carbon dioxide, and then you get, I believe, you get some H2O left, right? You get actually some HCCO3. I don't want to get too much into it, but as you can see, matters change because the chemical constitution, the chemical makeup of what you had at the beginning, the Alka-Seltzer and the water changes. Water becomes something else, right? And there's a release of gas. Release of gas, which leads to the next thing, right? State the main signs of a chemical change. They are. And Lavoisier realized that there's a few things. Change in color. Okay, that's one sign. Release of gas. Release of gas. Alka-Seltzer was an example, right? Changing color was the burning. I think you saw the video of the burning steel wool. Steel wool, changed color. All right, but also you also saw in the steel wool that it was there was very, very bright. So a release of energy. Release of energy is another sign. Okay. And one that you probably haven't done or seen yet is the creation of a precipitate. Precipitate is when you mix two liquids together and then a solid appears out of nowhere. Okay, that's but I don't think you've seen that, and you'll probably talk about that more later on. Okay, all right. So those are the signs of it, and that's Lavoisier did most of that, and Dalton. Okay, because they work with they work with gas a lot. Okay, let's go to the next one. The next one I'm reading right now. Associate the atomic model with the developers of it. This was my hopefully interesting class. I don't think many of you liked it, but it's okay. I liked it. All right. So we started with Democritus. So let me erase that. Okay, so we started the model with Democritus being a sphere, right? A small sphere, right? There were no scientific process, right? It was just a philosophical statement. Okay, then you go to Dalton. That's the exact same thing. Dalton is not written this way. I'm struggling with the eraser here. Don't judge me. Oh, why is it smaller? This is not good. Okay. Dalton. Dalton worked with experimental data. Okay. Both of them are hard, unbreakable sphere. Okay. All right. Experimental data with gases, H2O, CO2, CO, and a lot of different combination of nitrogen and oxygen. Okay. All right. So what happened after that? Thomson discovered electrons. Okay, I'm putting a e to the power of negative. That's how I always wrote electron. Please don't judge me. My wife does that already for all of us. Okay. So because of the discovery of the electron, they realized that this sphere could not be hard and unbreakable. Okay, it had to be mushy, right? It's a positive sphere with lumps, negative lumps in there. That's a Thomson model. Okay. So it is mushy and kind of dewy, right? Thomson's model. Then the next model is Rutherford. Why? Because he did the gold foil experiment, right? And the result of the gold foil, he realized that the atom is mostly empty space. That's why I'm making a circle that with dotted because it's empty with something very hard and positive in the middle. Okay, and you imagine those electrons were not lumps, but electrons were just moving around in orbits, like planets moving around a star. All right, that's Rutherford's model. All right, which is pretty cool. Which is a model that most people associate the atom being when they imagine the atom. That's pretty much what they imagine. Okay. So. Okay. I'm trying to figure out why that thing is so small. Okay. I was about to say, any question? You can't, you're not even there. Okay, so the next model is, but the problem with this model is that electrons would crash into nucleus. That's a problem. Okay, so Niels Bohr said that, well, the orbits are specific and defined, and electrons can only be here or here or here on those levels, but nothing in between. That's Bohr's model. Okay. What is interesting about Bohr's model is that it kind of builds into Thomson experiment. Okay, and if I can find a way to, awesome, to erase all that, I can show you what I mean. So Bohr's model. So we know when, and I made a little video about my own cathode ray, right? We know that Thomson, when passing electrical current throughout a gas, it created a light. But the question is why? Bohr model actually explains that. So nucleus. So what I'm going to do is put different 3 levels, right? So let's say the electron is in its ground state here, right? So ground state. And that electron receive energy. In which form? In different form. It can be electrical energy, just like the cathode ray, right? Or with a flame. I believe you saw a flame test when you put different chemicals under fire, and then it has different lights. Why does that happen? Why does in my video you see the tube with different lights? It's because if energy hits this electron right here, right? That electron will jump to a higher level. What we call the electron excited, and it goes to a higher level, which is called at this point the excited state. Does it stay there? It doesn't. Eventually, it goes back to its ground state. But while it does that, it releases photons. Not only photons, right? But photons of a specific wavelength. What does that mean, specific wavelength? It means that it's a specific color, which is why different substances, if you apply energy to it, will release color that are different because of their specific wavelength, specific color, right? So this is how the Bohr model explained this. And, and I think I just explained energy absorption and light emission, just like that, right? So, but why is it useful? Well, remember Thomson thought that electrons was light, right? And it makes sense to make that mistake because it seems like electrons are moving at the same speed as photons, which means electrons move at the speed of light, which is 3 times 10 to the 8 meters per second, right? So with that, you can make calculation using the speed of light, which is, we shouldn't be really using speed of light, but we should say here speed of photons and electrons being the same, right, is equal to the wavelength times the frequency. I don't know what frequency can either be shown as a F, can be shown as some weird Greek letter like that. I don't know which one you use. Use the one that you want, all right? So this is speed. Sorry, this is speed of light. This is the speed. This is the wavelength. And this is the frequency. Right? And this shows actually, if you would do a frequency against wavelength, an inverse relationship, which means that if the frequency goes up, the wavelength goes down. If you increase the wavelength, you decrease the frequency, which makes sense because if you have a wavelength like this that you pass through something, right? And you have something with a smaller wavelength, right? The one with a smaller wavelength will pass at the same speed many times here than here, right? Which is why a higher frequency means a higher frequency means a shorter wavelength, and a wavelength is the measure of a wave, right? Makes sense? I hope it does. I hope it does. And I apologize if I am incoherent, but I don't think I am. I'm so excited doing this. You guys have no idea It's much better at times than just harassing you for medical forms and making sure that you're wearing something Loyola on you. All right. And, and to finish with that, Max Planck, the life scientist, Max Planck. You can say Max Planck because in American way, because we're in America here, we say Max Planck, but really Max Planck. If you want to be, if you want to be hipster about it, or you want to be woke about it, you want to be a woke scientist, you say Max Planck. It's Max Planck. All right. So, Max Planck wanted to see the relation between the energy and the frequency. Oh, it's small again. Anyways, all right. So, and the frequency. So what did he do? He plotted energy. So he measured different frequency and calculated and measured the energy, the amount of energy. What did he get? A few things like that. He said, oh, that looks like a straight line. Yes, once again, energy directly proportional to Jesus fish appears once again here. All right. Energy is directly proportional to the frequency. How fantastic. That means you need a constant. Where do you find the constant? The slope of the graph. And that slope is equal to 6.62 times 10 to the negative 34. Weird number, but that's the number. And he said, well, I'm going to call this constant, very humble, this man, Planck constant, Planck constant, which is the H, right? I believe it's H. So you ended up with the formula energy is equal HF. So this is the energy. This is the frequency. And this is what we call Planck's constant. There you go. Historical review of your objectives. All right. I hope you enjoyed. And make sure you contact your teacher if you have any questions. All right. Thank you very much. Peace. Anna Kenyatta, you're a legend. I forgot to say that. You're all legends, but Hannah is an absolute legend. Okay, bye-bye.